far beyond our Sun lies a monster so vast it could swallow our entire solar system, VY Canis Majoris, one of the largest stars ever known. Tonight we'll journey into its burning depths to uncover what makes it so colossal. If you enjoy the wonders of the cosmos, please like, subscribe and share, and tell us in the comments what would you do if our Sun grew this big. Thank you for watching. Now let's begin. The outer dusty circumstellar reach around the red hypergiant VY Canis Majoris extends across distances measured in many thousands of astronomical units, and this broad region is where the most dilute material still associated with the star can be traced in scattered light and in faint emission. In this far field, the dust is extremely thin when compared to the dense clumps closer to the star, and yet the very fact that it is detectable at all implies that the star has undergone sustained mass loss for a very long interval. The star is located roughly around 4,000 to 5,000 light-years from Earth, in the direction of the constellation Canis Major. At that distance, the scale of the dusty environment appears as a subtle glow in imagery that integrates many exposures to reveal the wispy arcs that now mark the limits of the detectable circumstellar shell. The outermost dust is not smooth. It appears as a faint patchwork of small enhancements in density, interwoven with very low density voids. This is not a sculpted shell with a sharp edge, but rather a sprawling set of irregular shapes that only statistically trend toward lower concentration the farther one moves from the star. The dust grains here behave in the regime where interstellar influences begin to compete with or exceed any direct pressure or transient impulses from the star itself. This is a region where the star's distinct personal imprint begins to fade into the general environment of the Milky Way. The dust population here includes silicate-based grains that have formed in cooler material ejected long ago. These grains likely condense during episodes when gas expelled at high speed cools and transitions through temperatures where molecules can assemble into small solids. Over many thousands of astronomical units, the dust dilutes and is influenced both by any prior drift velocity imparted by ejection and also by gentle drag with the surrounding interstellar medium. The shapes that observers trace in high-sensitivity imaging are the result of a long accumulation of these influences. They are more like weathered relics of ejections rather than the crisp geometries sometimes seen immediately after a fresh outflow. The dusty matter in this outer region carries chemical and structural signatures that can be used to infer the thermal history of the gas and dust when the material was freshly ejected and cooling. However, in this far region, the dust is ancient compared to other layers and poorly constrained in timing, because dust at low density loses direct chronological markers. The outer dusty shell is also a natural interface between the environment, shaped by the red hypergiant, and the more uniform diffuse matter that fills the spiral arm in which the star resides. When researchers reconstruct the outflow history, they must consider that this outer region acts as a record keeper not of isolated events, but of persistence. This dust represents matter that left the star during phases so old that the star itself may not have been identical in temperature or brightness at those times. The reason this material still exists at such distances is because outward motion plus time has carried it far from the red hypergiant and into the periphery where the gravitational influence of the star and any radiative pressure it provides have long since become small compared to distributed galactic influences. In this region, the balance of forces is quiet. Turbulence is small. The local pressure of the interstellar medium is modest but non-zero. Ionizing radiation from the broader Milky Way or from nearby bright stars can still strike dust grains in this far field, but the intensity depends on orientation and whether a grain is shielded by other grains or larger structures. The pattern of dust here is not uniform, because the star does not lose mass in a perfectly symmetric manner. For reasons that are complex and linked to deep convection surface activity and episodes of eruptive ejection, the star does not deposit dust into space in even shells. Rather, the star's outer layers eject matter in arcs that emerge preferentially along hemispheric directions or along localized windows that open briefly during unstable atmospheric episodes. Over time, these arcs expand outward. Some collide with older arcs, some dissipate, some persist as faint filaments that can still be observed thousands of astronomical units from the star. The outer region therefore becomes a palimpsest of ejection events layered in three-dimensional space. From this distant vantage, the star's scale cannot be appreciated directly. The star itself is so small on this scale that it is completely unresolved in wide-field imagery of the outer dusty environment. Instead, the star is conceptually treated as a point buried deep within a vast nebular sprawl. If this dusty environment could be viewed from a vantage floating far above the plane of the Milky Way, the star might appear to sit within a faint localized puff of particulate matter, a tiny asymmetry in the otherwise nearly uniform brightness of the general interstellar medium. The dust distribution in this outer region is not solely shaped by ejection geometry. Over time, the star's motion through the host spiral arm also matters. Space is not static. The star moves relative to the background medium. Dust ejected in the past has been carried through interstellar gas, and this motion can cause subtle compression or distortion of outermost filaments, especially where relative velocities are not negligible. The direction of motion of the star relative to the surrounding gas may lead to a mild bow shape in the most distant structures. Yet in this region, the densities are so low that hydrodynamic shaping is not strongly pronounced. Instead, the combined signatures resemble a soft blur of particulate relics that whisper of the underlying violence buried much deeper within the inner atmosphere and nearer ejection zones. These dusty relics do not hint at future changes. They simply stand as diffuse testimony to ancient mass loss. There is no sharp environmental threshold one can cross in this region to demarcate where the star's personal sphere ends. It is more of a slow fade. At some distance, the interstellar medium becomes so similar to that which dominates the broader Milky Way that the signature of the red hypergiant becomes drowned in the general distribution of gas and dust that permeates this part of the galaxy. Observers are careful not to overinterpret fine irregularities because many filaments in the far outer region approach the detection limit and can confuse interpretation. Even so, the continuity of the extended dusty structure confirms that mass loss episodes in the past have carried material well outside the gravitationally bound zone of the star. All of this frames the circumstellar reach as the outermost stable zone of the star's dust domain. In this zone, the dusty material still surrounds the red hypergiant, but the trend toward lower density is still measurable, as one gradually moves inward from the vague edge that blends toward the interstellar medium. This region is still far enough from the star that the dust population behaves mainly as dilute particulate matter, but it is not as faint as the remote shell just described. Here the concentration remains small, but it becomes slightly more apparent in high-resolution imagery as low-contrast features against the background. Most of these grains are still cool and have existed for a long span of time. These conditions arise because the red hypergiant has been losing mass at different rates in different epochs, and each ejection carries outward gas that cools as it expands. Eventually, that gas sets conditions favourable for condensation of silicate grains, or at least for the survival of grains that formed earlier and have drifted outward over time. Thus, this region contains a mix of ages, It includes grains produced by older episodes that have drifted outward, and grains from later episodes that have only more recently reached this distance. The gradient in density is not linear. It is not a smooth diffusion from inner heavy clumps to outer dispersed grain fields, but a statistical trend in which certain directions contain slightly more dust than others. Differences in dust patterns hint at directional mass loss, where bursts of gas and dust emerge more strongly along one hemisphere or along some temporarily favoured outflow path. This generates an anisotropic distribution, where one direction can contain more dust than another at similar radial distances. This is consistent with observational inference that the star loses mass in irregular episodes. In this mid-outer region, the particles still form continuous swathes that cover large projected areas, but the dust does not exist in large continuous sheets. Instead, the configuration resembles a tapestry of small semi-coherent patches. When seen in scattered light, each patch produces only faint enhancement above the background, and any individual patch may include substructure. One must keep in mind that observation does not present a true three-dimensional picture. All these structures are projected onto a two-dimensional image plane. Thus, patterns that appear to be connected may not be contiguous in space. Certain faint portions of the dusty pattern only look adjacent because their projection overlaps. Where data from multiple wavelengths are combined, differences in scattering efficiency and thermal emission reveal that some patches contain grains of different sizes or slightly different composition. The star's motion relative to the surrounding interstellar medium also influences this density distribution, but here the influence is subtle. At this radius, the star's own wind or episodic ejecta still represent the dominant origin of the dust, but the relative flow past the surrounding interstellar environment can alter the shape slightly, especially over long timescales. The scale of this region can still be measured in thousands of astronomical units, but unlike the extreme outer edge where the dust nearly disappears into the general cosmic background, this mid-outer zone preserves a stronger statistical trace of origin. At these distances, the imprint of individual major outflow episodes can still be recognized, although the clarity of arcs and knots is weaker than in nearer clump zones. This region contains structures that may have once been denser layers that have since been stretched and diluted. Some may have collided or interacted with older material, forming blended textures. Over time, dust experiences weak dynamical effects that slowly reshape distributions. Radiation pressure from the star may have accelerated grains long ago, but the further out the grain moves, the weaker that influence becomes. In this region, the drift velocities imparted during ejection and acceleration are now primarily fossil signatures of what the star once did. The star is not static, it evolves. But the dust in this region is not evolving chemically with strong internal reactions. The grains are small solids that mainly interact with radiation fields and occasional collisions with gas. Over such long distances, the equilibrium temperature of dust can be low. That means infrared emission may help identify some portions of this field. However, the signal is not intense because the density is low. For observers, this region is useful because it is easier to resolve than the extremely faint far outer region, but it has not yet merged into the more complex and heavily structured zone that will be encountered further inward. The density gradient here suggests continued mass loss in the past, yet no precise timeline can be easily recovered without careful modelling. The reason is that gas ejected recently might mix with older dust, and the relative motion of the star through its local galactic environment might also influence how dust is distributed. Any attempt to use these structures to reconstruct specific past outflows must contend with the complexity that static morphology is the result of many processes acting over long time scales. The simplest inference is the one that treats this region as transitional. It is the portion of the circumstellar environment where the dust still clearly originates from the red hypergiant, but where the direct control of the star's current output and atmospheric activity begins to wane. This zone hosts grains that have travelled for a long interval, yet have not completely detached from the coherent distribution that forms closer to the star. It is a landscape of marginal association with the inner heavy clumps. Some of these patches originated as stronger features in the past, but have stretched and weakened as they migrated outward. As they spread, their optical depth decreases. They begin to exhibit a diffuse and almost cloudy geometry in imaging, but with subtle internal contrast. Observers treat this region as a coarse map that can guide where to examine more carefully when approaching the inner shell. This outer gradient area still requires careful sensitivity. The scattered light is faint. Many structures may appear only after long exposure integration. Certain wavelengths can reveal features more effectively than others, especially infrared wavelengths that trace warm dust. But here the dust is cooler than near the star. The distribution of thermal emission does not mirror perfectly the visible scattered light distribution. Where dust grains differ in composition or size, the scattering or emission properties change. That means patches that look dim at one wavelength may look slightly brighter at another. These optical differences do not imply major density differences. They may only reflect composition or grain size. In research practice, this region marks where modelers begin to transition from largely interstellar-dominated matter to star-supplied matter. In this transition zone, the identity of the star's outflow is still clear, but the imprint of ongoing or recent ejections is more blurred. It is fair to say that this region contains dusty record fragments that are neither old enough nor young enough to be categorized into one epoch, but instead represent a continuum. A calm survey of this sparse density gradient suggests that the environment is gradually becoming more structurally defined as one moves inward. At some point, the dust stops looking like an almost random glow and begins to develop stronger patterns. That point will be reached further in and with closer proximity to the red hypergiant. In this section, the gradient signals continuity and distance, but not the abrupt onset of dominant structures that characterize the regions to come. The dusty knots and clumps in this zone appear more distinct than the faint field further outward, yet still remain sufficiently diffuse that they cannot be mistaken for the dense features much closer to the red hypergiant. At these radii, the contrast of dust patches against the background is greater, and some knots display a gentle enhancement of brightness in scattered light images. These knots are not point-like. They have breadth measured in very large distances, yet retain edges that are statistically sharper than in the more dispersed zone beyond. These structures mark locations where the outflow of the star may have ejected material in bursts that had slightly higher local concentration or somewhat different temperature conditions at the moment of gas transition toward dust condensation. The star does not produce a steady uniform wind. Rather, the star undergoes variable mass loss, which can include eruptive ejection episodes. During such events, gas and dust can be expelled in more compact amounts along certain favoured directions. Each event's output disperses while travelling outward, but remnants of the initial concentration can remain visible as faint knots long after the event. The composition of these dusty knots is influenced by the chemical conditions that prevailed near the star at the time of ejection. Elements in the stellar atmosphere condense into molecules once the outflowing gas cools sufficiently, and then those molecules can form small grains. Silicates are common building blocks. Some fraction of the gas may carry heavier elements as well. As these grains travel outward, they become exposed to radiation fields that may change their surface chemistry. If the grains remain stable enough, They then continue to drift further out and join the population of dispersed dust. In this zone, it is still possible to detect clusters of grains that were once closer to one another and are not yet fully diluted. Because they hold a slight concentration advantage over the surrounding dust, the knots persist as features that can be recognized even after they have been stretched and eroded by time. The shape of knots is not uniform. Some appear elongated, others appear more roughly spherical. When the line of sight crosses a region where dust density is somewhat higher, the brightness of scattered stellar light increases slightly. These knots stand out because the viewing geometry happens to intersect greater dust density. The actual three-dimensional geometry may not be symmetric. It is often misleading to imagine these features as spherical bubbles. The red hypergiant has a complex history of mass loss, and this complexity can imprint highly irregular patterns. Data from multiple wavelengths reveal that knots do not exist in isolation. Some knots appear accompanied by small faint filaments that connect to larger features. Other knots seem to float without obvious bridging structures. The detection limits of imaging techniques also matter. Grains that too small or too cool may be invisible in certain wavelengths. Because of this, a region that looks sparse at one wavelength may look more structured in another. Such observational variations do not necessarily imply large physical variation in density. The knots represent a tracer of mass loss chronology, but also a reminder that the outward expansion of matter is not uniform. Clumps might originate from brief impulsive events, where material is expelled more strongly over short intervals. If several such events occur in overlapping directions and at different times, the resulting patchwork distribution will have complexity. Over large distances, the gravitational influence of the red hypergiant wanes. The dust in these knots is not gravitationally bound to the star. The knots simply travel outward through the surrounding medium. Collisions between grains are rare here. The density is low enough that most grains remain isolated. The knots are visibly denser only in the statistical sense. Rather than a continuous medium of greater density, the knot population represents distributions where the mean spacing between grains is slightly smaller than in the surrounding field. That difference is subtle, but statistically measurable in imaging with extremely long integration times. The velocities at which dust grains move in this region trace earlier acceleration. Radiation pressure and gas drag from the star likely imparted velocity near the time of ejection. As the grains travel outward, they carry that velocity, and since gravitational deceleration from the star decreases with distance, the motion can continue over long spans with only modest external influence. The surrounding interstellar medium can shape grains in limited ways. Gas drag may slow drift gradually, but the timescales are large and the effect may not be easily observable. Still, the ambient environment can exert a weak pressure gradient. Where the knots encounter slightly denser gas, they may undergo a mild compression. Where the environment is thinner, the knots may expand. Over time, these competing influences may change the geometry of the knots. However, these shapes still retain enough contrast that observers identify them as lumps in the overall dust field. The optical properties of these knots depend on the composition and size distribution of the grains inside them. Larger grains scatter visible light differently than smaller grains. If the grains are larger, they can appear brighter in certain wavelengths. The composition of the grains influences thermal emission. Grain chemistry influences how radiation is absorbed and re-emitted. In some wavelengths, these knots can appear warmer than the surrounding dust because they have slightly higher grain abundance and thus more efficient absorption of radiation from the star. But warmth here is relative. Dust in this zone remains cold when compared with regions near the star. The distance from the red hypergiant is so large that even diffuse radiation fields in the Milky Way may contribute comparable energy input to dust heating. The knots may include relics of outflows that produced more dust than average. Where ejection bursts were stronger, the departing gas may have cooled in ways that promoted increased grain formation. Thus, the knots tell observers something about the variability of mass loss. They testify to the fact that the star has not been shedding matter in a purely steady fashion. Variability in stellar winds and eruption events leaves behind inhomogeneous patterns. The fact that structures persist in this region means that the mass loss processes have been efficient enough to drive grains outward to these distances. Because these knots have travelled far, they represent matter older than the grains found closer to the star. However, their age cannot easily be computed. Without detailed velocity measurements and careful modelling, one cannot convert position into precise chronology. Even with such modelling, grain interactions with the surrounding environment would complicate the reconstruction. The best one can do is treat these knots as representatives of intermediate age dust, not as old as the far outer diffuse material, and not as young as the denser clumps deeper toward the star. They mark a portion of the circumstellar environment where the legacy of earlier eruptions remains visible. In wide-field observation, these features can be lost amid the general clutter of galactic dust. But with the right imaging tools and sufficient depth, the knots reveal that the star's history is encoded in these scattered lumps. The presence of these moderately enhanced clumps of dust suggests that the star's mass loss is not only episodic, but also directionally variable. And because the star is massive and already in an advanced evolutionary stage, the accumulation of such structures emphasizes how dynamic its outer envelope has been. These dusty knots do not forecast what lies deeper inward. They merely define the current observational transition from diluted outer dust to the more structured architecture that will soon become apparent. Shell-like arcs appear in this region as gently curved structures that indicate episodic ejections in the red hypergiant's past, and these arcs are among the clearest geometric signatures that the mass loss of the star is not continuous, but instead proceeds through discrete intervals of heightened output. The curvature of such arcs suggests that at the time of the emission, the ejection produced a roughly expanding surface oriented outward from the stellar atmosphere, and because different outflow episodes occurred at different times, multiple arcs can exist at different radii. The arcs in this region are not perfectly circular because mass loss is rarely isotropic. Instead, each arc displays variations in thickness, brightness, and continuity. Some parts of an arc are sharper in contrast, while other parts fade into the dust background, implying that the ejection itself likely had variations in density, or that later sculpting by the interstellar medium has blurred the weaker segments. The arcs persist because even though dust disperses as it travels outward, a sufficiently strong ejection event can impart enough coherence that the remnants remain organized into curved fronts, recognizable long after the event occurred. At this intermediate radius, these arcs are older than structures closer to the red hypergiant, but younger than the most diffuse relics at still greater distances. Their intermediate age means they present a useful context for interpreting the time evolution of mass loss. Observers can infer that at the time these arcs formed one or more mass loss episodes carried enough material outward in a broad directional sweep that the dust condensation zone downstream of the outflow produced a moderately uniform distribution of grains. As dust cooled and formed, the arc expanded and travelled outward. Over time, the arc's curvature remains visible because the dust inside the arc still has slightly higher density than dust outside. The arcs appear in a region where the brightness of scattered light is higher than in the diffuse outskirts, but not as high as in the dense inner clumps. Thus, these arcs are transitional signatures bridging the gap between loose knots, and the more dramatic structural complexity closer in. The existence of multiple arcs indicates that similar kinds of ejections occurred more than once. Each arc is a different snapshot of stellar behaviour, and while no precise chronology can be established without careful modelling, one can interpret these arcs as physical evidence of punctuated mass loss. The dynamics of how arcs form depends on how material leaves the stellar atmosphere. The red hypergiant is not stable, and large convective cells near the surface may carry energy from deep regions outward. If those cells become unstable, they can release enormous amounts of gas in localized outbursts. If those outbursts span a broad region of the photosphere, the resulting outflow can form an arc. That outflow expands, cools, and condenses dust. The resulting dust front becomes an arc-like structure. Some arcs may form when mass loss increases globally over a short interval, rather than when localized eruptions dominate. If this occurs, a nearly hemispheric outflow becomes possible. But because the star does not behave as a uniform sphere in flux and convection intensity, these arcs do not remain uniform shells. In practice, some arcs appear brighter in one hemisphere than another. Some arcs show breaks. Some arcs are only partially visible. Projection effects can also influence how arcs appear. In a two-dimensional projected image, a partial ring segment may look like a tilted ellipse or even an irregular streak. One cannot assume symmetry without careful three-dimensional modelling. The reddened and flattened shapes sometimes seen in images are due to the fact that arcs lie at various angles to the observer's line of sight. An arc that is circular in three-dimensional space appears as a projection that can be elongated. The detection of arcs in this region is particularly helpful because they provide spatial context for mass loss geometry. Their radial separation sometimes hints that the interval between major outburst episodes was substantial. If two arcs appear separated by a large distance, that might imply that one eruption occurred many years before the next. However, one cannot assign firm timescales simply by eye because the velocity at which arcs travel can vary. The red hypergiant may eject gas in one event at a faster velocity than in another event. Faster arcs travel farther in a similar time interval. Thus, a younger arc with high velocity could lie farther out than an older one that was driven outward more slowly. Without velocity measurements, each arc's true chronology remains uncertain. Still, the pattern of arcs suggests recurrence rather than continuous mass loss. This says something about the star's instability. Red hypergiants are known to be advanced in evolution, and large fluctuations in output can occur as the balance of radiation convection and gravity changes. The arcs in this region do not provide direct evidence of what the star's interior looks like, but they reflect the surface processes that resulted in large ejection episodes. The arcs also capture the cumulative effect of multiple cycles of dust formation. Some arcs may contain larger grains because conditions at the time of condensation favoured larger growth before outward drift froze the distribution. Others may show composition differences because the chemistry of the outer stellar layers changed with time. When comparing arcs, some appear more sharply defined than others. There are multiple reasons for this. The initial ejection might have been more coherent in one event than in another, or environmental interactions along certain directions might have eroded part of an arc more than another. Because the arcs are not rigid structures, they bend and distort slowly. Interactions with the surrounding medium, although weak, can carve subtle modifications into arc profiles. Also, arcs that move into regions of slightly different external pressure or density may experience small compressional or dilational effects. Such changes remain subtle and do not radically alter the arc shape, but over time they can affect the observable contrast in scattered light. Dust temperature in this region remains low, but arcs may be visible in certain infrared wavelengths because slightly denser regions absorb and re-emit radiation more efficiently than their surroundings. Thus, multi-wavelength observation can reveal arcs invisible in visible light, or visible arcs that look different in infrared, because dust composition influences thermal emissivity. Arcs formed during different outflow episodes might show slightly different brightness contrast in infrared. That difference does not imply strong temperature difference, but instead reflects how the dust interacts with radiation. Arcs in this region remind observers that mass loss is episodic. They depict layers of history. The existence of multiple arcs at different radii means that the star has cycled through repeated phases of outflow strength. Those outflows carry mass and also remove angular momentum. Over long evolutionary times, the cumulative mass loss shapes the star's next steps. Yet this region alone does not provide any prediction about future change. It simply identifies how the star's past has structured the present distribution. The arcs are quiet, geological-like timestamps in the dust environment. Each arc stands as a curved boundary between one mass loss episode and the next. One arc after another confirms that outflow is variable. These curved regions are not the densest features in the star's circumstellar matter. That region lies further inward. But here the arcs represent a tightening of the spatial coherence that was nearly invisible in the outer diffuse layer and remained only faintly present in the knot region. As one moves inward, these arcs become thicker and more coherent, until the dust environment develops even more distinctive structural patterns. Linear filaments and more intense clumps lie still closer to the star. But for now, the arcs define a region where episodic ejection episodes are recorded in geometry. The dusty folds in this region take the form of intermediate-scale structures, where the dust density is higher than in the arcs, but not yet as strongly sculpted as in the tight inner clumps, and these folds show gradual curvature or partial layering that hints at more complex interactions during outflow. The dust here often lies in sheets that bend or ripple, as though the outflowing material had experienced variations in velocity or density at the moment of ejection. The folds do not form perfect symmetry. Their contours are influenced by the geometry of the previous arcs, by the velocity profile of the current dust stream, and by small-scale interactions among grains and the gas that remains at low pressure in the outflow. These folds are thicker than the arcs but thinner than the deep clumps. They represent material that has travelled outward at velocities that are high enough to have left the near-star region, but not so high that it is already completely diffused into the outer envelope. Their presence suggests that the star may have undergone a longer period of enhanced mass loss, rather than only a brief eruptive spike. During a sustained high mass loss interval, the outflowing gas may form partially sheet-like structures. Dust condenses across these sheets over a range of distances from the star. Later, as these sheets move outward, folds appear because different parts of the sheet can travel at slightly different velocities. Differences in local density, dust composition, or grain size at the moment of formation could all contribute to how folds develop. Once the sheets begin to fold, the folds can break into smaller substructures. The folding may also reflect what happens when one outflow episode catches up to dust that formed in an earlier episode. If new outflow encounters slower older dust, the collision can compress or sweep the older material into a rippled layer. Over time, that rippling becomes visible as a fold. In some wavelengths, these folds produce brightness differences along their edges. When light from the red hypergiant hits these folds from various angles, certain regions scatter more strongly, producing a textured surface in visible light images. Infrared observations can sometimes reveal thermal emission that differs along the fold boundary. Subtle grain size differences can also influence how folds appear in different filters. Larger grains scatter light less efficiently at shorter wavelengths, but can produce stronger emission at longer wavelengths. These effects complicate interpretation. Scientific caution is needed to avoid assigning spurious features to density variations, when some features may reflect changes in grain properties. The spatial scale of folds suggests that this region formed during somewhat extended mass ejection periods. The red hypergiant may have spent increasing intervals in phases dominated by mass shedding. Such phases can accompany changes in interior energy transport or large convective cell turnover. If a convective cell grows and becomes unstable, it can deposit matter into the atmosphere that then is carried outward in relatively continuous outflow. That outflow forms dust once the gas expands and cools. Sustained mass loss can produce extended layers of dust. The strength of radiation pressure from the star at these radii continues to be weaker than near the photosphere, but enough to maintain outward motion. The dust in folds therefore retains some coherence as the outflow continues. The surrounding interstellar environment in this intermediate region remains low density but not negligible. Dust interacting with the ambient medium may undergo some drag. The drag is small, but over many years can shape fold geometry. Some regions experience mild compression if the star moves relative to the surrounding interstellar medium along certain directions. Over time, gentle compression along one boundary and stretching along another can impose additional ripples. This three-dimensional interplay produces patterns that become visible in high-resolution imaging. The folds are not monolithic. Some appear smooth, others appear segmented. Some show breaks where different materials meet or diverge. The star's outflow history is complex, and these folds reflect that complexity. The dusty folds bridge the region between the well-defined arcs that trace episodic events and the denser clumps that lie deeper inward. The folds can appear as semi-overlapping layers. These layers are evidence of evolution taking place on multiple timescales. The longest timescale pertains to the star's evolution. The surface convective activity is shorter. Superimposed upon these broad timescales are brief episodic events that produce arcs. Sustained heavy mass loss produces broad layers. The folds are the morphological result of this layering. Observers note that the folds generally appear more structured than the arcs. The folds preserve higher contrast. They represent stronger signals in scattered light. Many folds are thick enough to generate visible differential extinction, meaning that light that passes through them may be absorbed more strongly. The boundaries of folds also represent areas where dust grains pile up due to small gradients in velocity. Small differences in radial velocity can bring grains closer than average, producing a ridge-like concentration. Higher local concentrations in turn may facilitate the formation of features that can develop over time. In this manner, the folds serve as precursors to the dense clumps further inward. Each fold is like a sheet that has collapsed or bent until it begins to resemble a ridgeline. From that ridgeline, further evolution can produce small localized concentrations where chemical conditions or radiative forces focus dust. The folds represent a region of enhanced structural coherence. They bridge the purely diffuse outer zones to more substantial structures. The presence of folds at this radius shows that the red hypergiant has not only undergone episodic mass ejections, but also sustained intervals where mass loss persisted long enough to produce broad layers. That is consistent with an advanced evolutionary state, where the outer envelope is unstable. The red hypergiant is extremely luminous, and intense radiation fields from the inner layers continue to push material outward. But this region is far enough that direct radiation pressure is not as dominant as in the inner zones. the dust here continues to drift outward at velocity values that are now mostly inertial, the infrared emission from folds may show slightly elevated temperatures compared with the outer arcs. That difference arises because the dust density is higher and more grains can absorb and re-emit energy. But these temperatures remain low in absolute terms. The dust is not hot, it is only warmer relative to the far outer environment. These folds do not provide insight into what is happening at the photosphere or deeper. They are snapshots of how material has been arranged on the way outward. They reflect slices of the star's past behavior. In these folds, one can see evidence of how the star's mass loss rate fluctuated, how outflow velocities varied, and how the mixture of dust grain properties emerged. In the broader context of circumstellar morphology, the folds are a threshold. Beyond the folds, the arcs dominated. Within the folds, the clumps will dominate. But the folds themselves remain a midpoint in the journey from diffuse relics to dense, complex structures. Their presence demonstrates that outward flow is sculpted not only by discrete outbursts, but also by sustained phases of heavy output forming layers that ripple and break into stable but evolving sheets. In this region, the filamentary structures become the defining visual signature, and these filaments are among the most complex and delicate features in the circumstellar environment of the red hypergiant. Each filament is a narrow, elongated texture of dust stretched into thread like lines that twist, bend, and sometimes fork into substrands. Compared with the folds that lie farther outward, these filaments are narrower, sharper, and more sculpted. Their density is higher than the folds on average, and their linear geometry suggests that dust in this region has begun to respond more strongly to directional gradients in velocity or pressure. The star's mass loss history has produced a set of filaments that extend in distinct radial directions, and each one of these thin structures marks an evolutionary fragment of an outflow episode that was either more directed or more rapidly ejected. The filaments do not form as straight lines. They may arc or display irregularity depending on whether small variations in velocity push them slightly off trajectory. Because they exist in three-dimensional space, one should not interpret filaments seen in projection as lying on a two-dimensional plane. In reality, some filaments likely curve above or below others, even when the projection flattens them into a seemingly contiguous pattern. Filaments in this region mark locations where dust grains have been compressed into a long, narrow cross-section. The physical processes that formed these patterns could include the shearing action of differential expansion, where dust originating in slightly offset directions catches up with or diverges from adjacent streams. Shearing may produce a thin concentration front. The filament then persists because the grains in that region share similar velocity vectors, and as long as grains remain coherent over long durations, the filament maintains its narrow appearance. The dust in filaments appears in some wavelengths as sharply bounded streaks that are relatively brighter than their surroundings. Their brightness depends on how strongly they scatter incident radiation from the red hypergiant and how much dust is packed into the filament cross-section. Dust composition and grain size distribution also matter. If the grains are relatively large, scattering efficiency at visible wavelengths changes. Infrared emission also differs based on grain size and composition. This means that some filaments that appear weak in visible imaging may appear stronger in infrared or vice versa. Observers must be careful to interpret filament brightness correctly. A bright filament could reflect slightly larger grains or slightly higher density, not necessarily greater depth or thickness. The thermal environment in this region remains cold, but less cold than regions further outward. Because the filaments are denser, more grains are available to absorb energy from the star, and as a result the thermal emission may be slightly enhanced. However, these temperature differences remain small. Filaments also reveal that the mass loss history includes both impulsive and sustained phases. The folds represented sustained output. The arcs represented episodic bursts. The filaments represent directional persistence. A single filament might have formed when gas ejected from a localized region of the red hypergiant emerged with a velocity greater than its surroundings, forming a jet-like sheet of material. That sheet then collapsed into a narrow stream. Over time, the edges of that stream shear and disperse. But if initial coherence was high, the stream retains a strong identity long enough to be visible as a filament. The orientation of filaments can also reveal directional asymmetry. If filaments cluster preferentially in one hemisphere, that may indicate that certain parts of the stellar surface were more active. It may reflect that certain convective cells produced more energetic upwellings. Together, these filaments sketch a kind of directional memory of the star's unstable outer envelope. The star in this advanced evolutionary stage supports intense convective activity. Convection cells in very large stars can be enormous, with sizes on the order of fractions of the stellar radius. If one of these cells produces a large upward surge of matter, that matter can leave the stellar surface at a velocity that exceeds velocities in adjacent regions. This can produce a directional dominance that later appears as a filament. Because the red hypergiant is very luminous, radiation pressure aids in the continued acceleration of grains. Once grains leave the vicinity of the star and cool sufficiently, they become entrained in the outflow. The subsequent shearing arises because velocity fields differ slightly across the sheet. Where velocity gradients grow large enough, filaments develop. The filaments do not represent narrow cylinders of uniform density. Instead, they are statistically densest along their central lines, with density gradually decreasing outward into the surrounding dust. When observers examine filaments, they see that brightness decreases away from the filament spine. This implies tapered density profiles. Where the filament edges transition into the folds that lie outward, density decreases until no strong boundary exists. A filament is not a wall. It is a tapered beam of dust moving outward slowly. Over time, interactions with the ambient interstellar medium may stretch and warp these filaments. If the red hypergiant moves relative to the surrounding gas, the flow across these filaments may be able to compress their leading edges or stretch their trailing edges. Over extremely long time intervals, these interactions could distort filaments. However, current imaging captures them at a specific evolutionary moment in which they remain intact and distinct. Some filaments may show small subfilaments branching away. These branch points appear where the velocity field changed at the time of ejection. If a localized region experienced rapid sequential ejection events, then two or more streams may have emerged slightly out of phase with one another. Those streams can separate, forming two filaments that share a common base near their formation region before diverging. This branching provides additional insight into the star's behavior. It suggests that the process of mass ejection is not only episodic but also dynamically variable at short timescales. Such branching indicates that dust formation and outflow may proceed through sequences of intermittent bursts rather than a single uniform expulsion. In wide-field images, these filaments appear organized. They tend to radiate outward. This radial orientation arises because the source velocity vectors point away from the star. Because the star is the dominant source of kinetic energy in the system, dust moves outward more strongly along radial paths than tangential ones. If the star rotates, one might expect some twisting. But the scale of these filaments and the fact that many lie quite far from the star means that rotational effects may be tangled with other directional influences. The filaments sit in a region that bridges the folds with the dense clumps that lie further inward. The filaments have stronger density contrast than the folds, but not as extreme contrast as the clumps that lie closer to the star. They represent an environment in which directionality becomes more dominant and the complexity of shapes intensifies. These are narrow corridors of dusty memory. They document directional imbalances in the star's mass loss. They provide strong geometric proof that the red hypergiant does not shed matter in uniform shells. Instead, it produces beams of dust-loaded outflows that travel outward in roughly radial, but not perfectly symmetric paths. Each filament is a material witness of one or more strong ejection events that carried enough matter to form a thread of dust stable enough to persist. Filaments will not remain at this stage forever. They will continue to diffuse as they travel outward. Eventually they will transition into folds, then into arcs, and then into the most diffuse region. But now, in this radius, they mark the transition into the intensely sculpted inner dusty domain that lies even closer to the star. In this region, the asymmetric distribution of dusty outflows becomes clearly evident as departures from radial uniformity, and the filaments that once appeared like somewhat evenly spaced threads now reveal directional preferences that highlight how certain hemispheric zones of the red hypergiant have expelled matter more forcefully or more frequently than others. These asymmetries are not decorative irregularities. They are empirical expressions of physical imbalance in mass loss. The star does not empty its atmosphere in an even global manner. Instead, specific areas of the surface have apparently delivered stronger outflows that persist long enough in dust condensation space to create non-uniform concentrations. When observed from a sufficiently sensitive vantage-enhanced dusty structures toward one quadrant of the circumstellar domain signal, that the red hypergiant's mass loss history has included prolonged directional bias. In this region, the dust density is moderately high, and filaments have evolved into skewed patterns. Instead of radiating outward in a nearly isotropic fan of thin streaks, some of these dusty flows lean toward one hemisphere. That leaning can produce a cluster of filaments that share a similar direction. This clustering reflects the fact that at the epoch when these dust streams were expelled, the star had one or more strongly active convective cells whose upwellings were not evenly distributed. The star's surface is enormous. Convection cells in such a star can be enormous too, spanning regions of the photosphere that cover large fractions of the stellar surface. If those convective cells become unstable, and eruptive gas and dust flow from them in ways that reflect their geographic position. If several convective cells in one region become active within similar time intervals, the resulting dust output will appear as a directional excess. Over radial distance, the dust in those beams travels outward and forms one hemisphere with more dusty filaments than the opposite hemisphere. This gives an overall sense of imbalance. Such directional bias is consistent with the red hypergiant's evolutionary stage. The interior is undergoing changes in how energy is transported outward. It is in a late developmental phase where convection dominates large-scale behavior, and convection at these scales is not a mosaic of tiny granules, but a handful of large plumes. These plumes can be influenced by rotation magnetic fields and thermal gradients. Thus, certain regions of the stellar surface may deliver far more matter in outflows than other regions. Because the mass loss is not uniform, the asymmetry persists in the dust field. The dust in this region is denser than in the outer folds and filaments, but less concentrated than in the deepest inner clumps. Still, the density contrast here is substantial enough that brightness variations in scattered light and thermal emission can reveal patterns that stand out against the background. In images from different wavelengths, one hemisphere may appear more cluttered or more geometrically complex. that hemisphere may feature more overlapping filaments, more irregular boundaries, or more frequent branching. These visual differences are direct manifestations of how mass loss evolved over time. The dust in this region is old enough to have travelled a considerable distance, yet young enough that initial directional patterns remain visible. Observers note that these asymmetries can be persistent. They persist because the turbulence and drift at these radii are insufficient to erase directional memory. Collisions between grains remain rare. The density is not high enough for strong coagulation to cause grains to clump into larger aggregates that would even out conditions. Instead, the dust remains distributed roughly according to its initial source direction. Some gravitational influence from the red hypergiant still exists at this radius, but is vastly weaker than near the star. The dust is already in a more inertial regime. Drag forces from the surrounding interstellar medium are present, but are not large enough to uniformly shape the dust. Thus, inherent asymmetries in the dust field continue to drift outward along preferred directions. In some directions, filament clusters appear more complex than single filaments. These clusters may include multiple strands with slightly different thickness or grain distributions. When clusters overtake older dusty material, they can produce fainter shock-like boundaries. These boundaries do not appear dramatically curved like arcs, because the geometry of this region is dominated by directional beams rather than global shells. Instead, one sees elongated patterns where boundaries between dust streams appear somewhat jagged or diffuse. The internal composition of these streams may include mixes of grain sizes. Larger grains may drift outward more quickly or more slowly depending on their interaction with radiation pressure and drag. Because grain size distributions vary, some filaments that originate in the same direction may diverge slightly based on how grains respond to forces. This effect can contribute to the apparent widening of some clusters. It can also lead to subtle stratification, where smaller grains form more diffuse halos around the central beam. The directional asymmetry in this region is a crucial reminder that stellar mass loss cannot be viewed as a uniform global process. Instead, one must consider how convective and radiative influences shape local atmospheric conditions. Near the photosphere, convection transports heat upward. If a rising convective plume reaches a region where the gas can escape, that gas may be driven outward into space. When this process is more active in some hemispheres than others, dust formation in those hemispheres is enhanced. Outflow velocity may differ from one region to another. Over time, these differences lead to the filament clusters seen here. Even if a later phase of mass loss becomes slightly more isotropic, the memory of previous asymmetry remains embedded in the dust already launched into space. Observers who interpret these patterns must account for projection effects. Lines of sight that cross multiple filament clusters can create the appearance of increased density, even where true local density remains moderate. When mapping the circumstellar dust field, astronomers therefore rely on multiple wavelengths to distinguish overlapping structures from intrinsically denser regions. In this intermediate inner region, asymmetry dominates broad-scale interpretation. Some filaments may arc across one another to form crossing patterns. These crossings can emerge because of slight differences in velocity among filaments. If one filament started slightly earlier, or one had slightly higher initial velocity, that filament might be farther outward, even if both share similar direction. Thus, a faster filament from a later event might catch up with a slower filament from an earlier event. Once these filaments occupy similar radial distances, they can appear to cross. Such crossing structures may show mild compression at their interface, but dramatic collisions remain unlikely because the dust densities are too low. The crossing can still influence brightness. where two filaments overlap in projection, the combined optical depth produces slightly stronger attenuation of background light, enhancing contrast. Over time, these overlapping features yield a patchwork of line-like structures that reflect chaotic interplay of velocity vectors. The asymmetry in this region continues to remain stable enough that it is not erased. This asymmetry is directly tied to the star's past atmospheric dynamics. The red hypergiant's unstable outer layers set the architecture of the outflow. Because the convective processes in such a massive star are not gentle, the resulting outflows are not mild. They are powerful enough to eject gas and dust sufficiently fast that directional signatures persist even after the dust has travelled immense distances beyond the star's immediate gravitational sphere. In this zone, the complexity of directional asymmetry serves as a pivot between the narrower filaments that lie farther outward and the denser dusty knots and clumps that now begin to dominate closer inward. The next layers will show still greater coherence with higher density dust concentrations that develop when outflow funnels matter into tighter regions. But in this intermediate domain, the asymmetry of directional emission stands as the strongest visible marker of how unevenly the star has cast off its outer atmosphere. In this region, the dusty concentrations become high enough that optical depth increases significantly, and portions of the circumstellar field transition into domains where dust becomes optically thick, producing localized attenuation of the red hypergiant's visible output and creating irregular dimming that can be observed when viewing the star from afar. These optically thick dusty regions are not smooth layers. They present themselves as unevenly distributed clusters or sheets of material where dust grains have settled into concentrations dense enough that light from the star must either scatter multiple times or be absorbed and re-emitted at longer wavelengths before it can escape. In this domain, the dust does not simply trace outflow, it actively alters how the red hypergiant appears. The star's brightness at visible wavelengths may fluctuate because the line of sight crosses one or more of these concentrated dusty regions. Such dimming is not evidence of intrinsic luminosity variation in the star itself, but rather how the dust distributes along the line of sight. If the dust density fluctuates, the attenuation in visible wavelengths can fluctuate as well. Observers note that these variations can unfold over relatively short intervals. That does not mean that the dust itself moves rapidly. Instead, the apparent dimming depends on how small structural features in the dust pass between observers and the star due to subtle motions. Optically thick, dusty zones represent the first region in which dust plays a direct observable role in modulating perceived stellar brightness. Outside this region, dust mainly serves as a tracer of mass loss. Here, dust becomes a shaper of appearance. The high density of grains in this part of the circumstellar environment could trace back to several processes. Sustained mass loss events that create dusty folds can feed into funnel-like structures. Those structures eventually thicken enough to create concentrations of grains. Asymmetries described earlier can channel dust into certain hemispheres. As dust streams interact in this region, their edges can collide gently. Dust grains may not engage in strong collisions, yet even mild compression can enhance local concentrations. If grain sizes vary, larger grains may settle into slightly different locations than smaller grains. The slight gravitational influence of the star remains present at these radii but is weak. The dust is mostly in an inertial regime. Yet because dust streams sometimes overtake one another, local density can build up where velocity differences converge. In those zones, the grains remain more numerous than the surroundings, and thus the light that passes through these regions during observation becomes partially extinguished. The nature of extinction depends on grain size distribution. Larger grains scatter and absorb differently than smaller grains. The composition of grains matters as well. Silicate grains produce certain scattering signatures. If other materials are present, such as small inclusions of metallic compounds, the absorption and re-emission of radiation might differ. In this region, the dust is dense enough that scattered light radiates outward with broader angular distribution. Instead of reflecting light in a narrow cone, dense grain populations scatter in more diffuse patterns. That diffuse pattern manifests as extended structures in high-resolution imagery. These optically thick, dusty regions can display subtle color differences because visible light is attenuated more strongly at some wavelengths. When multi-wavelength observations are compared, the dust that causes strongest extinction in visible light may produce enhanced emission in infrared. This thermal emission emerges because dust grains absorb radiation from the red hypergiant and then re-emit it at longer wavelengths. The temperature of these grains remains low, but their emission profile reveals that they are warmer than the dust farther out. That warmth is relative and not indicative of high temperature. In this region, the density becomes high enough that radiative transfer processes become non-trivial for interpretation. Radiation does not pass directly through in a single free streaming line. Instead, radiation may undergo multiple scatterings. A beam of light from the red hypergiant that would escape directly into space in a less dusty region can here be diverted, delayed, or absorbed and re-radiated. This affects the star's appearance. When observers note irregular dimming, these optically thick, dusty regions are often implicated. The irregular nature arises because these dusty concentrations do not form perfect shells. They exhibit internal clumping. One patch might cause stronger attenuation than an adjacent patch, as these structures drift outward, or if the star gradually rotates relative to the observer. Small changes in geometry can cause one patch to cross a more direct line of sight. That action temporarily deepens the apparent dimming. Later, as the geometry evolves and the patch moves aside, the dimming recedes. These changes do not require large physical movement. Because the star is so large in apparent angular size from the dust's perspective, even slight displacement is enough to alter the amount of blocking along the line of sight. The optically thick zones are a powerful indication that mass loss has been especially intense in certain epochs. If the mass loss had always been mild and uniform, the dust would not concentrate enough to produce these strong attenuation effects. Instead, the star must have experienced intervals in which gas and dust production surged. Those intervals produced the raw material needed for high opacity structures. If the outflow then encountered density gradients within the circumstellar region, some of the dust may have been funneled into specific paths. These regions can grow in density if successive outflows deliver more dust onto the same path. Over time, the density difference increases until an optically thick region emerges. This region does not yet represent the densest part of the circumstellar field. Even deeper inward, the dust will accumulate into still more substantial clumps. But the optically thick zones mark the first region in which light extinction becomes a dominant observational effect. One must remember that these zones are not necessarily contiguous. They represent multiple discrete pockets or sheets. In high-resolution data, some appear like irregular islands in a sea of dusty streams. Some appear layered, others appear as overlapping shells. Projection can exaggerate these patterns. The true three-dimensional distribution may be complex. Infrared data can help to separate overlapping structures. Observers rely on both visible and infrared imaging to delineate which portions of the dust are responsible for the heaviest extinction. Optical thickness varies across the region. Some volumes are only marginally opaque. Others are deeply opaque. the transition between them may be sharp in projection. This area is important for reconstructing the star's episodic history. The mere presence of optically thick zones indicates multiple phases of mass ejection that yielded enough particulate matter to accumulate into these deep, dusty pockets. When future light from the red hypergiant travels into space, some of it will pass through these regions and alter the appearance of the star. The mass loss of the star, therefore, is not only an input to the structure of the circumstellar envelope, it also feeds back into how the star is perceived beyond that envelope. The optically thick, dusty zones serve as a direct intersection between the physical evolution of the star and the observational interpretation of the star's current state. They lie between filamentary asymmetry zones and the still denser inner clumps, forming a key threshold where extinction evolves into a pronounced radiative effect. In this region, the dusty environment transitions into the extended molecular layers, where the dusty medium gradually merges with cooler outer atmospheric zones of the red hypergiant, and here the material no longer behaves as loosely aggregated particulate outflow, but instead displays increased interaction between gas molecules and dust grains. These layers are not yet the photosphere where visible light is generated, but they represent a transitional regime where temperature, density and chemistry change in ways that are qualitatively different from the more inert, dusty structures farther outward. In these extended molecular layers, the gas is cool enough for molecules to form, yet still warm enough that the chemistry remains dynamic. Instead of entirely inert solids adrift in near vacuum, the dusty surfaces now interact with molecular species such as carbon monoxide and silicon monoxide. These molecules form when conditions allow chemical bonding to stabilize as the gas cools in the expanding outflow. Because molecules require specific temperature ranges to remain stable, their detection demonstrates that this region occupies an intermediate thermal zone between the cold outer dust field and the much hotter layers closer to the star. The gas density is higher than in the broad, dusty folds and filaments. The increased density facilitates more frequent collisions between atoms and molecules, which in turn enhances the probability of forming complex molecules. Yet the density is not so high that the region resembles a continuous fluid. The mean free path between collisions remains large compared to terrestrial standards. Still, the density is high enough that collisions matter to the observational signatures. In these layers, the infrared spectrum of the red hypergiant displays molecular features. The infrared emission from dust becomes stronger, and the rotational and vibrational transitions of molecules appear in spectra. These signals tell observers that molecules are present not merely as trace contaminants, but as a fundamental component of this domain. Because this region lies outward of the photosphere, the stellar surface is not directly visible here. Instead, the light from the star filters through these molecular layers. That light becomes partly absorbed by molecules. Then re-emission can occur at longer wavelengths. This influences how the star appears from afar. The chemistry in these zones depends on local temperature. Molecules that form here must withstand the radiation environment of the red hypergiant. Some molecules can be dissociated if the radiation is intense, or if collisions with energetic particles occur. But many molecules remain stable because temperatures are lower than the deep atmospheric layers. The distribution of molecular species is shaped by the outflow velocity field. Molecules may form in layers that correspond to the termination of certain convective plumes. In those regions, gas may have reached a temperature low enough for molecules to stabilize. When gas drifts outward, it can cool further, but if dust is present in the region, dust surfaces can catalyze the assembly of molecules. Dust surfaces can provide stable platforms where atoms collide, stick together briefly, and sometimes form molecules. These catalytic processes matter because they enable molecular formation to occur more efficiently than it might in free gas alone. The molecular layers are not uniform shells. In some directions, thicker molecular blankets exist. In others, the layer is thinner. Directional asymmetry earlier in the dust region persists in chemical form here. If dust in those directions condenses more strongly, then molecular formation on dust surfaces also becomes stronger. Observers detect an uneven distribution of molecular signatures. This unevenness is not noise, it reflects genuine structure. Many models of red hypergiants suggest that energy moves outward in giant convective plumes. Those plumes break the assumption of global spherical symmetry. The molecular structure reflects this asymmetry. The distribution of certain molecules such as carbon monoxide may differ from that of silicon monoxide. Their formation conditions differ slightly. Thus, their spatial distributions may not exactly coincide. Observationally, mapping different molecules presents a nuanced view of the extended atmosphere. The brightness temperature in these domains is low compared to inner zones. The gas emits via rotational transitions and does not produce visible light in the same way that a hot photosphere does. From a thermal emission standpoint, these molecular layers behave like semi-transparent blankets. They absorb and re-radiate infrared photons. When one region contains more molecules or more dust surfaces that hold molecules, the radiative transfer changes. Light from the underlying photosphere must pass through these layers. As a result, spectral lines in the emergent flux reveal the presence of molecules. Because these layers form a radiative interface between the inner star and the dusty outer envelope, they hold a key role in controlling how energy escapes. They are mediators of radiative transfer. The relative abundance of different molecules changes with radial distance. Closer to the star, the temperatures are too high for stable molecules to persist. In the outer dusty regions of filaments and folds, the gas may be too diffuse or too cold for new molecules to form. This intermediate region is therefore the zone where molecules can form and survive. The molecular layers also represent a storage site for chemical information about the red hypergiant's outer environment. The chemical composition of these layers depends on what elements are present in the outer star. Heavy elements that rose in convection plumes can appear here. The elements that condense into dust differ from those that form molecules. Some molecules form in the gas phase, then become attached to dust. Others form on dust surfaces. When molecules form, they carry isotopic signatures. These isotopic ratios document the nuclear processing history of the star. Thus, the molecular layers encode data about the stellar core, even though the molecular region itself is not the core. When deep convective cells transport material from inner layers toward the surface, some fraction of that material enters the molecular formation zone and becomes locked into stable molecules. In these ways, the extended molecular layers serve as a chemical archive. Although the observer sees only emitted or absorbed photons, that radiation contains microscopic detail about the star's elemental composition. Because this region lies between purely dusty structures and the photosphere, gas dynamics and radiation dynamics interact in complex ways. Radiative heating from the star influences how molecules rotate and vibrate, but because dust is present, dust grains absorb energy and re-emit infrared photons. The dust also shields some molecules from harsh ultraviolet radiation. Shielding is not perfect but partial. This shielding allows molecules to persist deeper inward than they otherwise might. The balance of shielding and heating determines where molecular populations are stable. These molecular layers do not yet produce the visible continuum. They operate mainly in the infrared. Their boundaries do not coincide with the visible surface of the star because that surface lies deeper inward. Instead, these layers serve as the transitional regime where chemical complexity emerges out of gas that was still too hot to form stable molecules closer in. As one descends further inward toward the photosphere, the temperature rises and the molecular constituents gradually dissociate. But that deeper layer lies ahead. For now, the molecular layers denote the final stage in which dust and gas remain chemically interactive. Here, the chemistry and the radiation together create a semi-permeable, radiative membrane around the red hypergiant. In this region, the material transitions into the extended molecular layers that sit just outside the light-forming boundary, and this domain represents the last chemically complex shell, where molecules remain intact before temperature rises inward to levels that begin to dissociate them, meaning this region behaves as a transitional envelope between molecular chemistry and the photospheric continuum. Here, dust still exists, but the relative role of dust as a dominant shaper of observed radiative transfer begins to change because gas becomes dense enough and warm enough that molecular bands in the infrared begin to saturate more strongly, and the radiative filtering of the stellar continuum by the molecular gas becomes more important than extinction from particulates alone. At these temperatures, many molecules remain bound, but some molecular species that were stable in the cooler layers farther outward begin to dissociate more frequently. The competition between formation and destruction becomes more dynamic. This produces a radial gradient in molecular abundance that depends sensitively on temperature. As gas approaches the photosphere, the increased radiation field, increased density, and increased thermal energy encourage dissociation of some molecular species, while encouraging the strengthening of others that require moderate but not extreme temperatures. Carbon monoxide is abundant and resilient to dissociation because its bond energy is high. Silicon monoxide remains significant, though its abundance can vary depending on grain formation. Water molecules can appear in some red hypergiant atmospheres if conditions occupy a narrow thermal window in which molecular formation can occur before dissociation dominates. Because the temperature inside this layer is higher than in the previously described extended molecular zones line opacities, in the infrared change strongly with depth, the continuum from the photosphere below is not yet visible as an unobstructed field because this region remains semi-opaque in many bands. Yet the continuum begins to emerge more strongly in wavelength windows free of strong molecular lines. Observers can detect these windows in infrared spectra as partial glimpses of the deeper layers. The emergent spectrum from this region contains broad absorption features caused by molecules. Those absorptions imprint onto the radiative output of the star. These features therefore contain diagnostic information about temperature, pressure, and composition. Because molecular populations depend on temperature in nonlinear ways, certain transitions appear strongly at one radius, but weaken rapidly as the temperature rises inward. This produces a layered appearance in spectroscopic maps, where one species dominates slightly above the photosphere and another species dominates slightly farther outward. That layering reveals a delicate structure to the intermediate zone between the dust-dominated envelope and the radiative photosphere. Dust still plays an important role here. Grains absorb and re-emit energy, providing a soft background field of infrared photons. Dust grains also continue to shield molecules from ultraviolet flux that would otherwise dissociate them. That shielding helps molecules survive further inward than temperature alone would suggest. But shielding cannot prevent dissociation indefinitely. As gas and dust descend further, heating increases. Molecular bonds break. The chemical diversity begins to collapse. The extended molecular zone is thus the last regime in which diverse molecules can persist in significant quantity. At these radii, the gas density becomes sufficiently high that collisions between molecules and atoms are not rare. Collisions influence rotational and vibrational energy levels. These collisions also help maintain local thermodynamic equilibrium for some species, meaning that the local conditions approximate a simplified relationship between temperature and level population. But while this equilibrium helps interpret spectra, the region is not homogeneous. Local differences in density, composition, and velocity can create subtle spatial variations in molecular opacity. The presence of velocity gradients means that line broadening can result from Doppler shifts. That broadening influences how absorption features blend together. The radiation field from the photosphere is strong enough to modify level populations. Radiative pumping can occur where the absorption of photons at one wavelength populates certain excited energy levels. That process modifies the emergent spectrum. Dust grains continue to carry surface chemistry. Some molecules form on their surfaces, others stick and then later detach. Adsorption and desorption compete. Temperature controls that competition. As temperature rises inward, desorption becomes more likely. Thus, dust may release molecules that it once carried. That release can modify the local gas chemistry. The interplay of dust surface chemistry and gas phase chemistry provides a feedback loop, even though the dust mass remains constant on short time scales. The extended molecular zone is dynamic on microscopic scales, even if macroscopically it appears as a steady transition layer. The total thickness of this layer depends on the characteristics of the red hypergiant. Larger stars with more intense radiative flux may host molecular layers that span large radial intervals. The presence of intense convection can also modify thickness. If convection cells push gas upward rapidly, the temperature gradient can sharpen, compressing the molecular zone. If convection is weaker in some regions, the molecular zone may broaden radially along those directions. Asymmetric convection therefore causes asymmetric molecular layering. Observations often reveal that some molecular species are stronger in certain hemispheres. That reflects uneven dredge-up of chemical elements in convection plumes. Deep convection transports not just energy, but processed material from interior shells to near-surface layers. When that material enters the molecular zone, it leaves chemical fingerprints. If such transport was intense on one hemisphere, that hemisphere may exhibit stronger molecular signatures for certain species. Mapping these chemical patterns thus provides clues to where major convective plumes have operated. Because molecular dissociation begins near the photosphere, the molecular zone acts as a filter that adjusts how much flux escapes into the dusty circumstellar environment. If molecular absorption bands are strong, less radiation escapes at those wavelengths. Then the dust farther outward sees a different spectral distribution than the underlying photosphere originally emitted. This means that the dust thermal balance depends partially on the molecular filtering above the star. Two identical dust grains located at the same physical radius, but lying beneath two different lines of sight with different molecular optical depths, may experience different heating. That difference can explain why some filaments or clumps in earlier sections show slightly different infrared emission, despite being at similar radial distance. Those differences do not necessarily imply different dust densities. They could reflect differences in the radiative flux that reached them, shaped by molecular absorption in the layer above. The extended molecular zone therefore connects inward radiative physics with outward dust morphology. This region shapes the radiation field that drives dust emission and influences the thermal evolution of the circumstellar envelope. As one continues inward, molecular diversity decreases further, because the temperature rises above stability thresholds and rotational and vibrational modes cannot remain bound. Eventually, the dissociation becomes dominant. That deeper region is the approach toward the photosphere, the zone where continuous radiation begins. But before that boundary is crossed, the extended molecular layers define the last stable environment where dust molecules, radiation and convection-derived mixing all operate together. In this region, the light-forming boundary emerges, and this boundary is the photosphere of the red hypergiant, the extended visible surface where photons detach from deeper radiative transport and begin free streaming outward. And here the radial scale of the star reaches roughly around 1,400 times the radius of the Sun, with acknowledged uncertainty, meaning that if the red hypergiant were placed at the center of our solar system, its photosphere would reach beyond the orbit of Jupiter and approach the distance where Saturn travels, although these comparisons must remain approximate because the exact radius depends on wavelength and on how one defines the optical depth that sets the effective light-forming surface. The photosphere is not a sharp edge, it is a layer where opacity declines to the point that photons escape. The substance here is not a solid surface, it is a deep luminous layer where gas is hot enough to radiate strongly, yet not so hot that atoms become fully ionized as they would in deeper layers. The photosphere in this region emits most of the continuous radiation that defines what observers perceive as the star's brightness in visible wavelengths. Temperature in this zone is high compared to molecular layers. Many molecules cannot persist here because the thermal environment is too severe for stable bonding. Instead, the dominant radiators include atoms and ions that absorb and emit in a dense forest of spectral lines. These lines sit atop the continuous emission. The photospheric radiation provides the energy that drives dust heating further outward. The radiative flux is vast. Light emerging here must pass through molecular layers above. Because those molecular layers contain strong absorption features, the emergent spectrum is modified. Yet the underlying continuum originates here. The photosphere appears bloated because the star is in an advanced evolutionary stage. The interior energy transport is dominated by convection in extremely large plumes. These plumes push outward, expanding the outer layers. This expansion reduces gas density in the photosphere, which then expands radially, until the balance between radiative force, gas pressure, and gravity stabilizes. That balance yields an enormous radius. The visible luminosity of such a star is immense. Radiation pressure from the photosphere pushes material outward. Some of that material may later condense into dust at larger radii. The photosphere itself contains convection cells that are immense. On a star this size, individual convective cells could equal a large fraction of the stellar disk. Thus the surface brightness may vary across the photosphere. These variations appear as bright patches or dimmer patches depending on where convection brings hotter or cooler gas upward. Observers may sometimes detect brightness differences across the stellar surface. They do not witness an even shell of uniform light. Instead, the photosphere is a dynamic surface where giant convection cells churn. The density and temperature vary across this region. If a convective plume rises strongly in one location, the gas temperature there may jump. That region becomes brighter. If a plume decays, that region darkens slightly. These changes produce surface irregularities in brightness. The photosphere is also the site where many spectral lines form. At certain wavelengths, the opacity is high because atoms and ions can absorb photons, promoting electrons into higher energy states. Those excited states later release energy via emission at slightly different wavelengths or by collisional de-excitation. Because the photosphere spans such a large radius, light from different regions of the stellar disk may pass through slightly different path lengths before leaving the star. That can introduce line broadening. Additionally, convective motions can imprint Doppler shifts. Gas that rises toward the observer imparts a small blue shift. Gas descending away imparts a small red shift. Averaged over the disk, these motions broaden spectral lines. The broadening provides insight into convective velocity scales. Because the photosphere is extended, the gravitational acceleration at this radius is weaker than near the base of the extended envelope. Gravity decreases with radius. That reduction influences gas pressure scale height. The atmosphere remains extended because gas is held in a more tenuous balance against gravity. This tenuous balance also influences how mass loss is triggered. It becomes easier for gas in the upper photosphere to escape. If convection drives gas upward fast enough, the gas may exceed escape velocity, or at least reach heights where radiation pressure accelerates it further. This is how the photosphere participates directly in mass loss. The mass loss seen farther outward originated in part from photospheric layers, but in this region the outflow is only beginning. One must remain within this current domain and not interpret the future of that outflow. Instead, this region is considered the route of radiative release. Particles that cross this boundary enter the state in which radiation is free streaming. The star's continuum emerges primarily in visible wavelengths, but also in infrared. The photosphere is hot enough to produce emission across a wide spectral range. The exact effective temperature depends on how one defines the photospheric radius. Red hypergiants have effective temperatures that remain low relative to many massive stars, but because the radius is enormous, the total luminosity remains vast. The photosphere can expand or contract slightly depending on thermal balance. If convection becomes stronger, the outer boundary may inflate marginally. If energy flux changes, the opacity structure may shift slightly. These changes occur over timescales that relate to convection and radiative adjustment. The behavior is dynamic but slow compared to the time it takes light to escape. Because the photosphere is a radiative frontier, the light that emerges must pass through this region before reaching space. The emergent radiation at this radius interacts with atoms and ions in the immediate region. The spectral line forest encodes details of temperature, pressure, and chemical composition. Heavy elements produced in earlier nuclear stages are present here at trace levels. Their absorption lines help researchers understand how material has been dredged up by convection. The interplay of convection, radiation, and chemistry becomes legible in the photospheric signatures. The geometry of the photosphere is nearly spherical, but not perfectly. Convection can deform the layers, but because the star is so luminous and the gravitational field is still substantial near this region, most deviations remain small. The enormous size remains the dominant structural fact. When comparing the star to the Sun, one must express size ratios in words and not in symbols. If the star is roughly around 1,400 times the Sun's radius, the implied volume becomes extraordinarily large. One must also recall that this radius is not fixed in a sharp sense. The photosphere is defined as the location where optical depth equals a value that allows photon escape. That value depends on wavelength. Thus, the star can have multiple radii defined in different ways. Some wavelengths may form deeper, some may form slightly outward. Observers interpret these with caution. Because this is not a rigid surface, the star's boundary moves when opacity changes, yet one can still define an approximate radius useful for comparison. From this region outward, the star's radiation shapes the entire dusty envelope. The dust that lies in later regions absorbs light released here. The irregular dimming from optically thick dust pockets is influenced partly by how much light emerges from the photosphere. In parallel, the molecular filtering just outward modifies this field. The photosphere therefore stands as the principal energy source that supports all subsequent interactions. It is the luminous foundation upon which the layered, dusty and molecular architecture rests. In these extended radii, the star simply radiates. The outward flow of photons defines how much momentum is deposited into the envelope. Dust grains at larger radii depend on the radiative momentum imparted here. For now, this region defines the observable surface where photons begin their journey into space. Below the photosphere lies the domain in which convective cells operate at such enormous scales that their horizontal dimensions can span significant fractions of the red hypergiant's visible disk. And in this region, these cells carry heat upward from deeper radiative layers, mixing material across great distances and supplying the photosphere with the thermal energy that ultimately becomes visible light. The gas here is hotter and more ionized than in the photosphere above, yet not so fully ionized as in still deeper layers where matter behaves in an almost plasma-dominated regime. These giant cells are not small granular patterns like those seen on the Sun. They are colossal energy pipelines in which hot gas rises, radiates part of its energy, at the photosphere cools and then descends again in vast sinking flows. Because the photosphere is extended, the convective turnover times in this region remain long, and the velocities vary with depth. Rising plumes do not appear uniform. Their mechanical behavior is influenced by rotation and magnetic fields. Rotation of the star is slow by compact star standards, but not negligible. The star's mass ensures pressure gradients that remain significant. Where rotation interacts with convection, some plumes may twist slightly. All these plumes ultimately deliver heat outward. In this region, the interplay between radiation and convection becomes more complex. Deep enough radiative diffusion dominates. Shallower convective mixing dominates. Here one stands at an intermediate regime where convection remains the primary means of transporting energy, but radiation contributes more than it does in even deeper layers. In this region, convection can drive local temperature fluctuations. Those fluctuations alter opacity. Because opacity influences how photons propagate, any local opacity changes modify how radiative energy couples to matter. Some regions may become more transparent, permitting radiation to flow outward more efficiently. Others may become more opaque, trapping energy that later may be released in a burst. Such local opacity fluctuations can contribute to episodes where mass loss becomes easier. When gas becomes heated and buoyant within one of these cells, it may forcefully rise, expand through the photosphere, and later join the molecular layers. This region therefore remains part of the engine that initiates outflow. One must still refrain from jumping ahead to the fate of that outflow. Instead, focus on the fact that these deeper layers set the conditions that determine how much energy is available to push gas outward. Chemical composition in this region contains signatures of nuclear processing from still deeper shells. Convection dredges up material from regions where helium and heavier elements may have been synthesized. When such material appears here, it mixes with unprocessed hydrogen-rich layers. That mixed composition modifies molecular formation farther outward once temperatures permit molecules to persist. Thus, chemical signatures in the molecular zone ultimately reflect chemical contrasts rooted in this region. Convective transport does not operate on rapid timescales. The star's envelope is large. Gas moves in enormous loops, rising slowly compared to human timescales, yet fast enough to matter for the evolution of the stellar atmosphere. The convective region also contributes to line broadening in spectra formed at the photosphere. Doppler shifts from upwelling and downwelling gas create measurable line asymmetries. Observers can use these asymmetries to infer average convective velocities. the convective cells deliver heat to the photosphere not in a uniform manner, but via a cellular mosaic, whose elements can be larger than entire orbits of inner planets in our solar system for comparison. In these conditions, the emergent brightness variations across the photosphere become directly linked to convective behavior here. Regions where convection updrafts deliver hotter material appear brighter at the surface. Regions where downdrafts sink cooler gas appear dimmer. These patterns are not static. They evolve over time. The life cycles of giant convective cells can last for significant fractions of a year or more. Their dynamics are slow compared to the flickering patterns seen on smaller stars. In this region, energy transport transitions from radiative to convective dominance gradually. Where opacity is high, radiation cannot escape easily. Gas then turns to convection as the efficient means of transporting heat. Buoyant parcels rise. That buoyancy is driven by thermal gradients. Rising parcels bring up both heat and chemical species. Once those parcels reach layers where radiative escape becomes possible, their temperature drops and they descend. The geometry of such motions is complex. In 3 dimensions, rising plumes may fork or merge. Downdrafts may form broad sinking flows. The entire system resembles a dynamic cycle locked into the star's deep envelope. Temperature and pressure remain very high here. Ionization fractions are significant. The electrons and ions contribute to large opacity coefficients. Because opacity depends on ionization state, any shift in temperature can shift absorption. In addition, the presence of heavy elements influences opacity through line absorption. The convective region therefore acts as a mixing mechanism that distributes those elements unevenly. Magnetic fields may form and dissipate here. Magnetic fields in a giant star can influence how convection cells behave. Magnetic tension may suppress convection locally. That suppression leads to changes in local energy transport. Regions where magnetic fields intensify may see reduced convective efficiency. Eventually the field dissipates and convection resumes. This interplay suggests that the convective region supports cycles of magnetic and thermal variation. Gas pressure remains immense. Even though density falls with radius here, the density remains high enough for collisions to be frequent and for matter to behave fluid-like. Radiative diffusion is slow because photons are repeatedly absorbed and re-emitted. This keeps photons trapped until convection transports them upward. Because the red hypergiant's envelope is extended, such radiative trapping amplifies the role of convection. In this region, the coupling between radiation and gas becomes close. Photons alter gas temperature. Gas motion alters opacity. Opacity alters radiation escape. This feedback loop shapes the luminosity of the star. When convection increases in one area, that area brightens at the photosphere. When convection decreases, that area dims. Over time, these brightness variations imprint the photosphere. When such patterns propagate upward through molecular and dusty layers, they may influence modest fluctuations in dust emission. It is essential to maintain spatial focus. In this region, the star's envelope transitions toward deeper radiative domains. The gas continues downward until a depth where radiative diffusion dominates completely. That deeper layer remains separate and will be the next stage. But here, where convective heat transport remains powerful and chemical mixing remains active, the region defines the last point at which matter participates in macroscopic circulation before energy transport transitions into the radiative regime. As one steps further inward toward hotter temperatures, ionization will rise, and matter will behave increasingly like radiative plasma. But in this region, convection is the agent that shapes structure. It is the pipeline for thermal energy. It is the mechanism that supplies the outer atmosphere with the heat that drives the entire circumstellar architecture. Below the giant convection cells lies a deeper region in which radiation and matter become so tightly coupled that the gas behaves as a highly ionized medium. And here the photons that will eventually feed the convective engine are repeatedly absorbed, re-emitted, and scattered by a sea of free electrons and ions. In this region, the temperatures are high enough that most atoms no longer retain all their electrons. Ionization fractions are large. Hydrogen is largely ionized. Helium is significantly ionized. Heavier elements contribute to bound, free, and free-free opacities. Collisions are extremely frequent. The local energy density of the radiation field is intense. Photons in this region travel only short distances before interacting with particles. The mean free path of radiation becomes so small that radiative diffusion must be described statistically. In practice, photons undergo random walk-like behavior inching outward over enormous times. This region contains the bulk of the star's internal luminosity reservoir. The nuclear burning shells deeper inward generate the energy, but the radiative zone here stores that energy, distributing it over large volumes and transferring it gradually outward. Convection remains active above, but here radiation dominates because the conditions favor absorption and re-emission. Density here is higher than in the convection-dominated layer above. Pressure also rises. Gas pressure and radiation pressure combine to support the star against gravitational collapse. Because the star is enormous, the gravitational well is deep, and the radiation field must be extraordinarily strong to prevent contraction. The combination of radiation pressure and gas pressure determines stability. In this region, velocity fields are weaker relative to convection. Gas moves, but motion is strongly damped by intense collisional coupling. Thermal gradients remain shallow enough that convection is inefficient. That is why radiation dominates. The energy flows outward through intricate interaction of photons with electrons and ions. As photons interact, they lose memory of their origin location. The spectrum of radiation inside this region approaches thermal equilibrium. The radiation field behaves nearly like a blackbody. The temperature rises sharply as one descends inward. The opacity remains large. Small changes in composition can influence opacity because heavy elements contribute strongly to line blanketing. Even trace amounts of iron group elements modify how photons propagate by increasing line opacity. That influence does not manifest as narrow lines here, because individual spectral features overlap heavily in these high-temperature and high-density environments. Instead, the cumulative effect of many overlapping lines modifies the opacity continuum. The structure of this region depends sensitively on how many heavy elements are present and on how they are distributed. Convection from shallower regions occasionally mixes heavy elements downward or upward, but overall mixing here remains less vigorous than above because radiation pressure and density gradients restrict large-scale flows. Gas may oscillate slightly. Local instabilities may form, but these remain modest compared to the convection above. The star's mechanical behavior in this region is governed by hydrostatic equilibrium. Gravity pulls inward, pressure pushes outward. The star must balance. If pressure falls, the region contracts slightly, raising temperature, increasing pressure, again restoring balance. If pressure rises, the region expands slightly, cooling, reducing pressure. This dynamic stabilizes the layer. Because ionization depends on temperature, a small rise in temperature can increase ionization, increasing electron density, modifying opacity. This feedback influences the temperature gradient and can either promote or suppress additional radiative diffusion. Deep in this region, the coupling of radiation and matter becomes so strong that the two behave almost as a single thermodynamic entity. Radiative heat capacity becomes significant. The radiation field stores large amounts of energy. Gas and radiation exchange energy continuously in collision-dominated conditions. Because the photons escape only slowly, changes in luminosity from below do not appear at the photosphere immediately. The enormous optical depth between this region and the photosphere imposes a delay between energy generation and radiation escape. Energy that originates in deeper nuclear burning shells may take long intervals to diffuse outward. That delay means the radiative zone acts as a buffer. It smooths out fluctuations. It prevents most rapid variations in luminosity from passing upward. It defines the long-term brightness stability of the red hypergiant. The region also contains gradients in chemical composition. The star has undergone earlier nuclear burning stages. Helium enrichment may exist relative to primordial hydrogen. Heavier elements may be present because convective dredge-up from still deeper shells has occurred at some point in the past. These composition gradients influence opacity. They influence density. They influence how radiation diffuses. In analytic models of massive star envelopes, this region determines how energy transport splits between convection and radiation. But in this specific region, radiation dominates. The radiative flux is so large that convection cannot compete. Only when the temperature drops enough outward and opacity rises enough to impede radiative transport does convection begin to dominate again. Thus, in this area, the boundary between convection above and radiation below is set by the opacities of partially ionized elements. Those partial ionization zones can cause local opacity peaks. Such opacity peaks sometimes promote convection in red supergiants, but the present radius of the red hypergiant is so large that the region of partial ionization lies outward. Here the ionization is more complete. Ionization also influences sound speed. In a fully ionized gas, the sound speed can be high because temperature is high. High sound speed modifies propagation of acoustic waves and internal oscillations. Those oscillations may couple weakly to the envelope and produce low-frequency pulsations at the photosphere. In this region, turbulent motions become small relative to thermal velocities. The gas behaves like a radiative plasma. Collisions transfer momentum efficiently. Electrons and ions remain well mixed. The radiation field shapes the thermodynamic state. Because this region couples nuclear burning to the outer layers, it serves as the thermal engine's gearbox. Energy flows outward in a structured manner because matter here must obey radiative transfer laws. Closer inward, nuclear burning shells drive energy production. Closer outward, convection lifts energy upward. This region connects the two regimes. Its thickness is enormous. Its energy density is vast. Its physical state is dominated by ionization and radiation interaction. It is functionally invisible to direct observation in visible light, because photons that originate here cannot escape directly. They must scatter upward through photosphere and molecular layers. But spectroscopic interpretation of the star's integrated output hints at the conditions here because line blanketing and luminosity patterns depend on the radiative diffusion. In massive evolved stars like this red hypergiant, the radiative zone sets the stage for how the star evolves toward later nuclear burning episodes. The full details of those deeper processes lie inward of this radiative domain, but this region defines the last buffer between the observable world of the photosphere and the nuclear structure that will appear further inward. Here the gas is hot, ionized, dense radiation filled and in thermodynamic near equilibrium. It is the star's radiative furnace and the final calm zone before entering the nuclear burning shells that lie still deeper. Still deeper inward lie the nuclear burning shells in which successive layers of fusion convert one set of nuclei into another, and here the temperatures and densities rise to such extreme values that the structure of matter becomes determined by nuclear reaction rates, rather than by the radiative or convective transport regimes alone, meaning this region is where the star's energy originates in its present stage of evolution, and where each shell corresponds to a different combination of temperature, density, and available fuel. In the outermost of these nuclear shells, hydrogen fusion may continue if pockets of hydrogen remain, but in a red hypergiant of this scale, hydrogen fusion is expected to have migrated inward from earlier evolutionary stages to deeper regions, and helium burning may dominate some shells. In those shells, 3 helium nuclei combine to form carbon, and under still greater temperatures carbon captures helium to produce oxygen. Deeper shells may engage in carbon fusion, where carbon nuclei combine to produce neon sodium or magnesium, depending on reaction channels and available density conditions. Deeper still, neon burning can occur when conditions allow neon nuclei to photodisintegrate into oxygen and helium, which then recombine. In still deeper shells, oxygen burning occurs in which oxygen nuclei combine through reactions that yield silicon or sulfur. Still deeper silicon burning operates near the highest temperatures within this shell-structured zone, producing iron group nuclei that represent the most thermodynamically stable products under these conditions, because fusion beyond iron does not yield net energy. These shells do not operate as freely mixed layers. Each shell occupies a radial band where temperature and density exist in equilibrium with the gravitational potential and the local nuclear reaction rate. Because the star is so massive and large, the nuclear burning does not occur in a single region, but in multiple adjacent shells, each one closer to the core representing a more advanced fusion pathway. The reason shells form is that fusion reactions require specific combinations of temperature and density to proceed efficiently. As one moves inward, temperature increases. Reactions that require lower temperatures occur farther out. Reactions that require higher temperatures occur farther inward. The shells are arranged in order of increasing reaction difficulty. The burning shells interact through radiative and conductive energy transfer. Heat flows outward. That heat energizes the overlying shells. The shells remain in approximate hydrostatic equilibrium. Gravity compresses the inner region strongly. Gas pressure and radiation pressure push outward. Together these forces define the shell boundaries. Within each shell, the nuclear reaction rates are extremely sensitive to temperature. A small increase in temperature can dramatically increase reaction rates. Such sensitivity introduces feedback. If reaction rates accelerate, they generate more energy. If the energy cannot escape efficiently, the local temperature rises further. But because the star must maintain hydrostatic equilibrium, the shell expands, slightly reducing density and tempering the reaction rate. This regulatory mechanism maintains relative stability. Fusion timescales vary depending on which reaction chain dominates. Hydrogen fusion operates slowly in main sequence stars but more rapidly in evolved giants due to higher core temperatures. Helium burning proceeds faster. Carbon, neon, oxygen, and silicon burning operate progressively faster still. The deeper shells may operate on very short timescales compared to hydrogen burning earlier in the star's history, yet one must remain in the present layer without stepping beyond. These shells constitute the source of the luminosity that spreads outward through the radiative region above. They determine how much energy is available to drive convection in the outer layers. They determine how much radiant energy arrives at the photosphere. Their reaction products influence composition. Heavy elements produced here remain in the interior until convective dredge-up events, or mixing at boundaries transport these elements into higher layers. Over long intervals, some of those heavy elements will contribute to the chemical composition, detected in molecules farther outward, and to solid grains in the dust envelope even farther still. The nuclear shells are arranged in a nested pattern, hydrogen burning outermost if present in the stellar interior at this stage, helium burning interior to that, carbon burning deeper, neon burning deeper yet, oxygen burning still deeper, then silicon burning near the innermost envelope region, where nuclear statistical equilibrium approaches ion group synthesis. These shells remain separated by steep gradients because reaction cross-sections depend exponentially on temperature. The material in these shells is highly ionized. Ionization ensures that electrons and ions behave like a plasma. The nuclei behave in a state where thermal velocities approach fractions of the speed required to overcome Coulomb barriers. Nuclear reactions do not occur through cold fusion. Instead, quantum tunneling permits charged nuclei to overcome repulsion at these temperatures. The resulting fusion releases energy. That energy appears as kinetic energy of reaction products and as gamma-ray photons. The gamma-ray photons quickly interact with the plasma transferring energy to electrons, then to ions. That energy becomes part of the thermal reservoir. It then diffuses outward in the form of radiation field energy. In these nuclear shells, composition gradients appear. As burning proceeds, some fuel becomes depleted. Some products accumulate. When enough products accumulate and conditions permit further fusion, the location of burning moves inward. That motion is not mechanical displacement, but a shift in the radial location of reaction equilibrium. The thickness of the shells depends on opacities, temperatures, and densities. Some shells may be thick, others may be thin. The geometry remains spherical to first order because gravitational fields maintain symmetry. Rotation and magnetic fields may induce minor distortions, but the nucleus of the star remains dominated by hydrostatic pressure. Conditions here exist far beyond everyday comprehension. Pressures are immense. The gas behaves as a degenerate plasma, in parts where electron degeneracy may influence the equation of state. Degeneracy pressure can moderate contraction. But in a red hypergiant, the envelope remains so extended that inner burning shells may not yet be dominated by degeneracy in the same manner that a compact core would be in later stages. The nuclear burning shells define the engine of the star. They supply the energy for the outward luminous journey. The material in these shells constitutes a layered record of how far nuclear evolution has progressed. Each shell signals a stage in which a particular fuel remains abundant enough to ignite. Though one must refrain from jumping ahead, the nuclear shell region defines the interior domain, where matter is rearranged by fusion and where energy enters the chain of outward diffusion that ultimately becomes the light released at the photosphere. These shells represent the deepest zone to be described in this series of layers. Deeper inward still lies the innermost central domain. That region contains the core, but the present region remains the last where shell burning dominates. Here the structure is a network of nested fusion layers, each defined by temperature, density, and composition. They generate the radiant power that sustains the enormous brightness of the red hypergiant. In this region, the interior of the red hypergiant reaches the innermost central domain, where the nested nuclear burning shells converge toward a core that now supports the most extreme thermodynamic conditions in the entire star. And here the density is highest, the temperature is highest, and the equilibrium between gravity and pressure sits in its most precarious configuration, because this central environment is the anchor of the entire stellar structure, and the region on which the entire layered system above ultimately depends. The core exists in a state of remarkable compression. gas behaves as a plasma in which electrons, ions, and radiation are so tightly coupled that the state of matter must be described through high-temperature nuclear physics, rather than through simplified collisional gas models. At this depth, gravitational forces drive inward with overwhelming intensity. The pressure that counters this collapse is derived from both thermal pressure and radiation pressure. The core is not a single homogeneous fluid in the ordinary sense. It is a region characterized by extremely high densities in which nuclear reaction pathways form the structural backbone of the energy generation process. The production of energy here feeds the nested nuclear shells surrounding the core. Each shell outside this region receives part of the energy flux from the core and uses it to maintain its own nuclear burning processes. Because all energy generation ultimately rests on this deepest zone, the core determines how rapidly the star evolves. In this region, nuclear statistical equilibrium dominates. That means the distribution of nuclei tends toward the set of species that minimize free energy under these temperature and density conditions. Iron group nuclei are abundant in this environment because fusion reactions that produce nuclei heavier than iron do not yield net energy, and thus iron represents a final resting point for nuclear reshuffling. The free energy minimum does not imply chemical inertness. It implies thermodynamic equilibrium under extreme conditions. The energy reservoir here is concentrated. Thermal particles collide at energies that exceed nuclear Coulomb barriers. Gamma-ray photons are abundant. The pressure exerted on the core boundary by the radiation field is vast. Radiation pressure supports the structure. That pressure is coupled to the gas and to the composition of the plasma. If the radiation pressure dropped significantly, the core would contract. That contraction would increase temperature. That temperature would then raise reaction rates. This feedback ensures approximate equilibrium. The stability of the core does not mean stasis. The nuclear reactions continue. They rearrange matter from shell to shell as conditions require. The star's total supply of fusion fuel is finite. The burning of successively heavier elements yields higher temperatures and shorter timescales. This region produces energy that takes long times to diffuse outward. That ensures the luminosity of the red hypergiant remains high. The energy that originates here must pass through the radiative zone above, then through the convective zone, then through the photosphere, then through the molecular layers, then through the dusty envelope. The core therefore sits as the deepest and most fundamental driver of the entire circumstellar architecture described. The magnetic field in this region remains strong because it is produced by currents in ionized plasma moving under extreme density. The dynamo may be suppressed or enhanced by certain flows, but the magnetic field does not dominate the structural dynamics in this region. Instead, magnetic couplings operate as corrections. The poloidal and toroidal components of the magnetic field can interact with differential rotation if present, but gravity and pressure remain the primary equilibrium forces. The core's rotation is slower than the outer layers in some models, but not negligible. The degree of differential rotation within the core influences internal mixing of nuclear products. And because convection may not penetrate deeply into the core at this stage, most of the mixing that occurs within this region is diffusive rather than convective. The composition is defined by the end state of nuclear burning. Iron group abundance is high. Some lighter nuclei exist in boundary layers between shells. But the core's interior composition is stable relative to the evolving shells overhead. Because the red hypergiant is well into advanced evolutionary stages, the core's structure is highly temperature sensitive. A small temperature increase can trigger large increases in reaction rates. But hydrostatic equilibrium ensures that such temperature increases become self-limiting. If a rise in reaction rate generates more energy, The core expands slightly. That expansion reduces density. That reduction in density slows reaction rates. The result is quasi-stability. The timescale of change remains long relative to dynamic timescales. The core therefore exemplifies a balance between nuclear energy generation and gravitational confinement. In this state, the core defines the final interior environment before any future core transformation events occur. But the rules of this narrative require that one remain in the present region. Therefore, no future transformation must be inferred or described here. Instead, the focus continues on the nature of the present core as the present origin of radiation that supports the star's luminosity. This region contains all that is needed to explain why the red hypergiant is luminous, why it drives an expansive photosphere, why the molecular layers exist as chemical intermediaries, and why dust can form in the outer atmosphere. The core's existence makes all outer architecture possible. Without the density, temperature, and radiation produced here, the star would not inflate to such a large radius. The star's convective envelope would not operate. The photosphere would not radiate. The dust fields farther outward would not exist. The entire circumstellar environment described above is downstream of this central engine. The core's equilibrium is the anchor on which everything is built. Because matter and radiation remain fully intertwined here, the core represents the most complete form of matter-radiation coupling in the star. Though photons escape only after long intervals, the energy distribution remains steady. Because this region is not observable directly through visible imaging, the evidence for it arises indirectly through spectroscopic interpretation and through theoretical modeling of stellar structure. Observations of line blanketing at the photosphere and mass loss at the outer envelope both reflect energy flows that originate in this region. In theoretical models, the core's temperature composition and density define the burning rate. From that burning rate arises the luminosity. That luminosity then determines how far outward the star's atmosphere expands. The appearance of the star as a red hypergiant with a radius so large that it exceeds the orbit of Jupiter emerges partly because this core's energy production is immense. In this region, the boundary between thermonuclear physics and macroscopic astrophysical structure disappears. The nuclear reactions produce photons. The photons apply pressure. The pressure shapes the star. The star shapes the dusty envelope. The dusty envelope shapes observed brightness. All of these feedback loops converge on this deepest interior domain as the source of energy at all radii.